We decode the molecular architecture of spider silk, where liquid proteins transform into crystalline structures stronger than steel. We trace this evolutionary engineering from ancient fossils to modern biomimicry, revealing how orb weavers manipulate kinetic energy. By analyzing these microscopic tensile wonders, we bridge the gap between biological survival and advanced structural physics. The impossible material comparison. This tiny strand is 5 times stronger than steel, yet it starts its life as a liquid. We are decoding the molecular architecture of spider silk to reveal how nature turns liquid proteins into crystalline armor. It is an engineering marvel that has outpaced human technology for millions of years. The evolutionary engineering mystery. Hidden within the webs of common orb weavers lies a secret of physics that dates back to ancient fossils. How do these tiny creatures manipulate kinetic energy and structural physics with such precision? We are tracing this biological journey to see how spider silk is currently revolutionizing modern biomimicry and construction. The microscopic deep dive. Beneath the microscope, a spider's silk reveals a complex world of tensile wonders that bridge the gap between survival and advanced science. We are analyzing the liquid-to-solid transformation that allows these biological structures to absorb massive impacts without breaking. Discover why the future of our skyscrapers might be hidden in a spider's web. Discover the incredible biological feat where liquid protein dope stored in the abdomen instantly solidify into high-performance fibers. Examine the molecular shearing process where the spider's spinneret acts as a natural particle accelerator to align protein chains. Analyze how this phase transition allows the silk to remain flexible yet poses a tensile strength that rivals high-grade carbon steel. Shift focus from the fiber to the frame as we break down the kinetic energy absorption of the classic radial web design. Explore the difference between stiff structural dragline silk and the microscopic glue droplets used to snatch prey out of midair. Observe how spiders tune their webs like musical instruments to sense vibrations and locate structural weaknesses in real time. Trace the evolutionary timeline back 380 million years to see how primitive silk evolved from simple burrow linings to complex aerial traps. Compare fossilized silk samples with modern specimens to understand why this biological tech has remained largely unchanged for eons. Investigate how environmental pressures forced spiders to develop distinct silk types for underwater diving bells and high-altitude ballooning. The biomimicry revolution. Move from the natural world to the laboratory where 2026 breakthroughs in CRISPR technology are finally allowing us to mass-produce synthetic silk. Review the latest applications in sustainable aerospace composites and biodegradable medical sutures that outperform traditional plastics. Detail the challenge of replicating the spider's low-energy manufacturing process to create a new generation of green structural materials. Imagine a world where we build skyscrapers and bridges using the same principles of microscopic crystalline alignment found in webs. Discuss the potential for living architecture, where structural components can self-heal and adapt to external stress like a spider's silk. Synthesize the lessons learned from nature's greatest engineers to project how biophysics will define the next century of human innovation. Please like and subscribe to my channel, and press the bell icon to get new video updates.